when I look at our next speaker, I know he knows virtually everything about mechanical engineering. And I think that California's program would not have evolved to the point that it did without the remarkable technical know-how that Michael Jackson brings to the table. He has his advanced degrees from Berkeley in mechanical engineering. I was looking this morning at some early work he had done 30 years ago advising the Congressional Budget Office on methanol technology. So we're lucky to have such a wealth of experience and knowledge reflected in this guy. So with that, I want to welcome my friend Michael Jackson. Thank you, Michael.
Thanks, Paul, for the kind introduction, and thank you, Carbon Recycling, for putting on this symposium, and Casey for inviting me here to come and speak. I'm currently doing small consulting, so the company I'm with now, the company I founded is MDJ Research. Formerly, I was the head of a larger consulting firm in California, Accurex Environmental, to various names of the corporate superstructure had changed, but the first was Accurex Environmental, the last was Tiax. And we really specialized in trying to understand how to get alternative fuels into the marketplace. And the basis for our work was understanding the technical feasibility, then going out and demonstrating that technical feasibility, showing what the benefits of the alternative fuels were, and then finally trying to figure out how to get those alternative fuels into the marketplace, be it incentives or other market-based approaches. So that's my background. And what I wanted to do today was to kind of go over some of the methanol experience from my perspective, talk a little bit about where we are with methanol today, and my perspective is really going to be based more on the U.S., where we are in the U.S. I understand that, and we've heard this morning a lot about what's happening in other regions. I also want to talk a little bit about greenhouse gas reduction pathways and how methanol might play into that, and then finally conclude with an outlook. So, in the early 80s, California embarked on a program to try to reduce petroleum consumption in its transportation market. That was started with a feasibility study which I headed at Accurex Environmental, where we looked at all the different fuels, and one of the clear winners were the alcohols compared to, at that time, electricity or natural gas, specifically compressed natural gas. And one of the key things in the California program was to look at the total barrel of oil concept. So if we were going to put something into the light duty sector, it also had to be viable in the heavy duty sector. So we wouldn't have this imbalance of reducing, for example, from the refineries the gasoline product, and then also not reducing the diesel product. So the California program really looked at a broad spectrum, not only from light duty to heavy duty, but also stationary applications. We demonstrated, for example, a number of gas turbines that operated on methanol, generating electricity. The first vehicles shown in the upper left-hand corner here were dedicated methanol vehicles. I think these were like M90 at that point. Both Ford and VW participated in that. Technical success, but really an issue relative to consumer acceptance because there was very little infrastructure. So we primarily aimed these vehicles at fleets. But we did have times when people, because of range anxiety, would actually leave their vehicles on the freeway because they thought they were going to run out of fuel. That led us to more of a flexible fuel vehicle strategy. And also at this time, the automotive industry was changing considerably, so a lot of electronics were coming on board. So instead of having very complicated carburetors, which you'd have to adjust the fuel ratios with levers and chains, you could now all do this electronically. And that technology was really developed out of Ford. And that was fairly successful in terms of getting into the market. We ended up with a fairly large fleet in California towards the middle of the 1990s. And then on the heavy-duty side, we were one of the first to demonstrate methanol in transit buses in the San Francisco Bay Area. We actually had 2 manufacturers participate in that program, MAN in Germany and GM Detroit Diesel in the US. And that program actually expanded across all heavy-duty engine manufacturers. So we had Cummins participate in that with a technology that was using Avocet, which was a cetane improver, added to the methanol. We had Ford participate with an SI M85 technology in a medium-duty truck application. We had Navistar participate with a glow plug type technology. So it included all the major manufacturers. What came out of that, sort of the legacy that's still there today, even though the methanol did not go forward, was that corporate average fuel economy, so-called CAFE incentives, were developed out of that program. The deal that California struck with Ford was if Ford would build the vehicles, California would lobby to get incentives that would allow the auto manufacturers to take advantage of basically having a alternative fuel vehicle, whether it used the fuel or not, be rated at a much higher fuel economy than the gasoline version. So there was a large incentive for the auto manufacturers to build these FFVs. They were first methanol, and then as methanol faded, mainly due to the fact that methanol was used as MTBE into the gasoline pool, the ethanol flexible fuel vehicles then became popular in the US. The population of those flexible fuel vehicles now is upwards of 20 million vehicles, albeit little E85 or ethanol is, neat ethanol or high blend ethanol is used in those vehicles. The key to me is that those vehicles come at very low incremental cost. And we already heard how important that is for the consumer relative to his buying decisions. And I'm going to talk more about that later. So today in the US, most of the ethanol is used as E10 at a relatively low octane. 10% ethanol is blended in with reformulated gasoline blend stocks to meet the RVP requirements throughout the state. So in California, for example, most of the time we run at a 7-pound RVP. The rest of the US is up around 9 pounds. Putting 10% reduces the emissions, particularly of some of the toxics, just by dilution. So you're diluting the gasoline, benzene emissions go down. There is a small but growing E85 infrastructure, but as I said, because of price at the pump, most of the times it is not priced where consumers are actually going to buy that fuel. And primary reason is that ethanol is sold into the energy market versus into the consumer market, from my perspective. So the value as blended at E10, it's valued on a volume basis. If you wanted to sell it at E85, it had to be valued on an energy basis. And that's the issue that the ethanol producers are dealing with. There's also a spec now out that now defines E85 as M51 to E83, or ethanol, E51 to E83. So, what's the current interest in methanol? Work that I've been doing with Fuel Freedom, I'm currently their director of research, has shown that methanol can be a viable alternative to meet the goals of petroleum displacement, which is really the objective of Fuel Freedom Foundation, is to displace petroleum in the transportation sector, and lower emissions of greenhouse gases, criterion toxics emissions. And why is this new? For us in the US, there was a substantial increase in the natural gas supply due to the shale exploration and production. And second major point, which was pointed out this morning already, is that the work by Jamie Turner and his colleagues have shown that GEM fuels, gasoline, ethanol, methanol, can be demonstrated in existing ethanol FFVs, and I'm going to talk a little bit more about that. And then finally, meeting the climate change objectives is going to require large reductions in the GHG impact of vehicles. So very briefly, this chart here shows the price difference on an energy basis between petroleum and natural gas. And although the current trend is downward in terms of the delta, you can see that in the early years, natural gas and petroleum were priced approximately the same, even though one has more utility than the other. And then after the large run-up in oil prices, that price differential became quite large, which then opens up the possibility of using natural gas in the U.S. to produce a fuel, particularly methanol, that would be cheaper at the pump than, or at least compete with gasoline. GEM fuels. It's probably hard to read this a little bit, but the key points here is that the octane is approximately similar through all these different blends. The heating value of the fuel is similar. Okay, the heating value is important because if you have a less heating value, it would mean you have to inject more into the cylinder to get the same power. So you don't have to change the injectors, for example. And then there's just other advantages to these various mixtures of fuel. So, in fact, a GEM fuel is really transparent to the ethanol FFVs, provided you don't exceed, say, 56% methanol into the gasoline. So that's important because we have, again, in the U.S., 20 million of these vehicles out there operating. So you have an existing fleet that potentially you could sell methanol into, provided you could show that the emissions performance of these ethanol FFVs is the same as emission performance will be with these GEM fuels. The work by Turner and his colleagues has shown that the tailpipe emissions look good. In fact, sometimes they're even better relative to NOx emissions, for example. I have not seen any evaporative emission test, and that's one part of the research that needs to be looked at more closely, is taking existing U.S. FFVs and running them through the U.S. emission procedure, including the FTP tailpipe as well as the evaporative emission standards. There's also the possibility, again because of the flexibility of the control systems on these vehicles, that you could convert existing gasoline vehicles. Now the OEs don't necessarily like conversions, and I get that. You want to sell new cars. But it's a possibility that you could convert by simply changing the software on a gasoline vehicle to operate as a flexible fuel vehicle. And Fuel Freedom has at least shown that to be feasible for one vehicle. It was a GM vehicle we did, and that conversion was on ethanol, but I would suspect that the same performance would be seen for methanol. So that would also help you have a fleet of vehicles, not only the FFVs, but converted vehicles, which then would create a demand for the fuel that you could put into the infrastructure. I'm going to talk about natural gas to different fuels here and focus on that just because that is probably the most near-term viable option, although from a mass market point of view in terms of scalability. I realize that there are biofuel options that could be considered here, going to these fuels. But for the time being, let me just focus on the natural gas to various technologies. So you could take natural gas to electricity, and then run that in a battery electric vehicle, or run it into a plug-in electric vehicle. You could take natural gas, convert it to methanol, use an internal combustion engine, or you could take the natural gas and actually go to synthetic gasoline, or you could go to ethanol, albeit that's going to take more energy to get to those two end-use things, also used in a IC engine. Or you could use natural gas and liquefy it, or compress it and also use it in IC engines. Or you could take natural gas and produce hydrogen and then go to the fuel cell vehicles. The internal combustion engine could be improved in terms of its efficiency, as Leslie has already talked about. So downsizing, turbocharging, using a high-octane fuel to increase the compression ratio, downspeeding, plus then starting to electrify. That might be an option that would get us to very low greenhouse gas emissions, potentially at a cost that's a little bit cheaper, maybe not a little bit cheaper, but at a cost considerably lower than an battery electric path or a fuel cell path. What I've shown here is, on the left-hand side, gasoline. So you have a fleet average gasoline at 2005 on the far left. And then you have typical, this is sort of a mid-size passenger car, typical 2005 pass car, port fuel injection technology. And then what happens if you start doing advanced technology on the gasoline vehicle and you start electrifying the platform, and eventually you go to a PHEV with high octane fuel. You can see the red line represents an 80% reduction, which we have quoted before as what you need out of the transportation sector to get to a point where you are stabilizing the CO2 emissions in the atmosphere. So you can see that you get fairly close just on gasoline, provided you have a high octane fuel and that you have in gasoline. Now for ethanol, you can do the same thing. That's the yellow bars. And then methanol gets a little bit better than the other ones. So there's not so much a difference between gasoline, ethanol, and methanol. The question would be the cost to the consumer at the pump. And I would suggest that natural gas to methanol, based on the spread that you saw previously, could be a cheaper at the pump fuel for the consumer. On the right-hand side, you can sort of see the gold standards, right? There's hydrogen, fuel cell, and there's electricity, battery electricity. Those are zero-emission vehicles. But even the gasoline technology today, meeting US Tier 3 standards, are very, very low in terms of emissions. You're talking, every standard has a 0.0 in front of it in terms of gram per miles. This is a lot different than it was 30 years ago. So the marginal improvement from the gasoline or the ethanol or the methanol vehicles to the zero-emission vehicles is not as large as it was 30 years ago. And the benefit, therefore, may not be worth the cost that you have to put into it. So let me kind of summarize where I think we are on alcohol vehicle technology. I think it could be the most cost-effective GHG reduction strategy. It minimizes battery costs on the vehicle, which is a high-cost component. The key is having an enabler, a high-octane fuel that you can design around. You can design the IC engine with higher efficiency. So the ethanol, the higher ethanol and methanol blends make some sense there. You could also do it with gasoline. I think that's going to be more expensive if you do not use the ethanol methanol. There's some talk in the US of doing a 30% ethanol blend, which sort of optimizes the octane rating of the fuel. So that's a possibility. The problem with that approach is that it requires the US EPA to recertify that fuel as a new gasoline, and that takes time. They already have a fuel out there that is acceptable, and it's E85. You could run that at E51, for example. So high efficiency ICE coupled with electrification, I think, is a cost-effective pathway to achieving GHG reductions, as I showed in that previous slide. It needs to be DI, turbocharged, downsized, downspeed, high compression ratio. So this would be a vehicle, this would be a fuel, an engine that is designed for that fuel. It's not flexible fuel at this point. It's designed for that fuel. You need to minimize both from a consumer perspective, there needs to be a value proposition here, and you need to minimize both the fuel and the vehicle cost. So high octane may be an option, but I think it's going to be more expensive than the alcohol options. Ethanol or methanol may be the best fueling options, either in low-level blends like the E30 or the higher-level blends. I suggest that the higher-level blends make more sense just because of the regulatory issues associated with making a EPA in California judgment on substantially similar to gasoline. But with all that, if you're going to electrify, you still need to minimize the cost of the batteries. So, I think methanol can be price competitive at the pump. That has to be there for the consumer value proposition. In my experience, we have, through the California and through all the alternative fuels we've tried to introduce in the United States, it's great that we have lower emitting fuels, cleaner fuels. It's great that we have lower greenhouse gas emission fuels. And we put incentives around the higher cost of the vehicles. But like here in Iceland, look at what the penetration rate is for those fuels. If you want to really hit the mass market, you're going to have a fuel and a vehicle, and the best option would be have low-price fuel and low-price vehicles out there for the consumer to accept it. You don't really have to go through all this payback period, which tend to be long, and it tends to get confusing to the consumer. So, market methanol to existing and converted FFVs could establish a fuel demand. We're going to have to solve any material evaporative emission issues. Some of that work is already happening in Geely, for example. And it sounds like it's already happening at Fiat Chrysler, too. The U.S. is very close to adopting a new methanol spec, ASTM 5797, which parallels the ethanol spec in that it defines fuel methanol as M51 to M85. That's important because, again, the flexible fuel vehicle fleet out there could run something around M56. So that allows methanol to take advantage of that. The next step would be to introduce a dedicated high-efficiency ICEs using methanol and really take advantage, as Leslie has shown, of the fuel properties to maximize the ICE efficiency, and then integrate that and couple it with electrification to the platform, be it starting off with start-stop, hybrid technologies, or the ultimate competitor to hydrogen and battery electrics, which would be the plug-in hybrid electric vehicle. So, thank you for your attention. For those of you that would like to visually see some of the history that's happened with methanol in the States, I encourage you to look up this movie that was produced by Fuel Freedom. It's called Pump. It's available on iTunes and Netflix. So
our plant is in there.
Your plant is in there. So again, thank you for your attention.
Thank